Hello everybody! In the previous video, you started to learn about points and vectors in two-dimensional space. In this video, we're going to continue learning about vectors in two-dimensional space. Last time, we ended up by speaking about a vector operation called vector addition. So given two vectors, v and w, remember, we write vectors with lowercase letters and an arrow above it, and we use angle brackets to distinguish vectors from points, and we often use subscripts so we don't run out of letters. Given these two vectors, vector v equals v1, v2, and vector w equals w1, w2, we defined the sum of the vectors, vector v plus vector w, we define that to be equal to the vector with components v1 plus w1, v2 plus w2. And adding vectors, as you may suspect, is one of the fundamental operations we're going to do with vectors. The other very important operation we're going to do is something called scalar multiplication. So given a vector v and a number c, and in this context, the number c is often called a scalar, I suppose to distinguish it from a vector, but c is just a number. We define the scalar multiplication c times the vector v to be equal to the vector c times v1, c times v2. In other words, we multiply both parts of the vector by c. So, as some examples, 2 times the vector 3, 4 is equal to the vector 6, 8, because 2 times 3 is 6, and 2 times 4 is 8. You can multiply by negatives if you wish. Negative 3 times the vector 1, negative 2 is equal to the vector negative 3, and negative 3 times negative 2, that's 6. So the result is the vector negative 3, 6. Finally, 1/2 times the vector 5, 4, well, multiply each of these times 1/2, and we'll get the vector 5/2, 2. That's scalar multiplication. It's like multiplication, but twice as much fun because you get to do it twice. Now, scalar multiplication does not change the slope or the direction of a vector. Last time, we talked about the slope of a vector v. If the vector v has components v1 and v2, we defined the slope of v to be v2 divided by v1, or you might have heard of rise over run from an earlier algebra class. Now, that's the slope of the vector v. What's the slope of the vector c times v? Well, each one of the components gets multiplied by c, so according to that formula, the slope is going to be equal to the second component divided by the first component. In other words, c times v2 all divided by c times v1. In this case, the c's cancel, and we're left with v2 over v1, which is the slope of our original vector. In other words, it just doesn't change the slope. However, it does change the length. So, for example, here's a vector v, the vector 4, 2. I've drawn that in blue right here. If I take the vector 4, 2 and multiply it by 2, 2 times v is 8, 4. If I were to graph this, and I'm drawing this vector with its initial point at the origin, if I were to graph this vector, it's pointing along the same direction, but it's twice as long. If I took this vector v and multiplied it by 1/2, right, 1/2 of the vector 4, 2 is the vector 2, 1. And if we were to graph this, I get this smaller red vector right here, which is half the length of our original vector. If we were to take the vector v and multiply it by -1, we would get the vector -4, 2, which, well, it's pointing in the opposite direction. It still lies along the same line, which has the same slope. It's just facing in the other direction. That's the vector -4, -2. So in general, when you multiply a vector by a constant, that's going to change the length. Remember, the symbol for length of a vector, we use this double bar notation. The length of the vector, c times v, is equal to the absolute value of c times the vector v. And if c happens to be negative, then the direction reverses. So for example, over here, when we multiply by -1, the negative means the direction reverses. The length of the vector is +1 times v. In other words, the length didn't change for this orange vector down here. So in summary, multiplying a vector by a constant c, multiplying it by a scalar, scales the vector. That is, it either stretches or shrinks the vector by the absolute value of c. So that's scalar multiplication. Now, if you want to, you can actually check that the length of c times the vector v is equal to the absolute value of c times the vector v. And checking that these statements are true just requires some algebra. You would algebraically simplify each side just to see if they're equal, which, spoiler, they are. On the left-hand side, we have the length of c times the vector v. C times the vector v, that's the vector c times v1, comma, c times v2. To find the length of a vector, it's a square root of the first component squared plus the second component squared. And so we have this square root, then the sum of squares. Now we can simplify this even more, because if we have a square of c times v1, that's c squared v1 squared. And the same thing with the second component. That becomes c squared v2 squared. These two terms, well, they have a c squared in common, so I could factor out a c squared from these two. And there's a rule for simplifying square roots that says if you have a square root of a product, if I have a square root of c squared times this, I could make that, well, the square root of c squared times the square root of this, and it looks like I forgot to write a little bit here. This should be v2 squared right here. v2 squared. So if you're taking notes, please be sure to add that in. But the square root of c squared, that pops out as a factor of absolute value of c. Right? The absolute value is when you square c, right, any negative sign disappears. And so we have an absolute value there. The right-hand side of this expression, the absolute value of c times the length of v, well, we can immediately write down what that is in simplest form. It's the absolute value of c times the length formula. But that's exactly what you got when you simplify the left-hand side. This is v2 squared. So the left side is equal to the right side. That just verifies that it's equal. Now, here's an interesting fact. This will turn out to be extremely useful later on in this video. If you take a vector and you divide a vector by its length, the result is going to be a vector with length 1, which is called a unit vector. For example, let's say you start with a vector 3, 4. I like this vector because it's easy to calculate the length. The length of the vector 3, 4 is 5. Right? It's a 3, 4, 5 right triangle. 3 squared plus 4 squared is 25, and the square root of 25 is 5. So the length of this vector is 5. What happens if we divide the two entries by the length, right? Or equivalently, what if we multiply it by 1/5? 1/5 times the vector v is the vector 3/5, 4/5. And then if you calculate the length of this vector, there will be some fractions involved, but you'll find that the length of this vector is the square root of 9/25 plus 16/25. If you work that out, you'll get the square root of 25 over 25, which simplifies to 1, as we expected. As a slightly more complicated example, where the numbers don't work out quite as nice because of a square root, let's say you have the vector w, the vector 2, 3. The length of this vector is the square root of 2 squared plus 3 squared. That works out to the square root of 13. If you take the vector w and divide both of these by the length, so divide 2 and 3, each by the square root of 13, and then you find the length of this vector, you're going to find that it's equal to 1. So for any vector, you can kind of shrink it down usually by dividing out by its length, so it has this length of 1. We'll see how that's useful in just a moment. Now, seems like we're going to switch gears for a second here, but this will all come together momentarily. Just as a quick trigonometry review, in case you haven't done any trigonometry lately. And trigonometry is all about right triangles. So given a right triangle, right, so you have a right angle, the side opposite the right angle is called the hypotenuse. And let's call one of these angles of the triangle, let's call it theta. The other two sides of the triangle, the side which is next to theta, that's called the adjacent side. And the side, well, the remaining side, is opposite from the angle theta. We call that the opposite side. You define the trig functions as ratios of the sides of a triangle. So the sine of this angle is defined to be the length of the opposite divided by the length of the hypotenuse. The cosine of this angle is defined to be the length of the adjacent side divided by the length of the hypotenuse. And the tangent of this angle is defined to be the length of the opposite side divided by the length of the adjacent side. And there is a mnemonic some people like to use to remember these ratios. Take the first letters here, SOHCAHTOA, and some people remember the mnemonic word SOHCAHTOA. Whatever helps you remember these is fine. Now, one way this is helpful is to help specify the direction of a vector. Now, you can specify the direction of a vector in a few ways. One way we talk about it is the slope, the rise over the run. Right? That was v2 divided by v1. But you can also specify the direction of a vector as the angle it makes with the x-axis, with a horizontal axis. To calculate this angle, you just need a little bit of trigonometry. In particular, if this is the vector v1, v2, we're going to draw this vector as starting from the origin. If the vector is v1, v2, then that means you've gone across v1 units and up v2 units, which gives you two sides of a triangle, and the vector itself is the hypotenuse. And we want to find this angle here. This is the angle between the vector and the x-axis. The known information is the opposite side and the adjacent side, which means it's easiest to use the tangent to figure out this angle. The tangent of this angle, as we said before, the tangent is the length of the opposite side divided by the length of the adjacent side. In this case, the opposite side has length v2, and the adjacent side has length v1. So the tangent of this angle is equal to v2 divided by v1. Or, if you're a fan of slope, the tangent of this angle is the slope. There's a really close relationship to directions, right? The slope is just the tangent of the angle that it makes. Now, if you want to solve for the angle, you can use the arctangent or inverse tangent. So theta is arctangent of V2 over V1. And if you're using a calculator or a computer, just keep in mind that the trig functions usually use radian measure. So look out for that. All right, so that's how you can calculate the angle that a vector makes with the x-axis. Now here's something very interesting. What if you have this right triangle, right? Again, you have this angle theta, the adjacent side, the opposite side, and the hypotenuse. What if the hypotenuse has length 1? Well, then the trigonometric formulas get even easier. If the hypotenuse has length 1, sine theta is opposite divided by hypotenuse. But opposite divided by 1 is just the length of the opposite side. Similarly, again, assuming that the hypotenuse is equal to 1, the cosine of theta is defined as the adjacent length divided by the hypotenuse length. But if the hypotenuse is 1, you have adjacent divided by 1, which is just equal to the length of the adjacent side. So if the length of the hypotenuse is 1, then sine theta is the length of the opposite side, and cosine theta is the length of the adjacent side. In other words, we have this picture right here. If we have a right triangle, and the hypotenuse has length 1, and this angle is theta, then the length of the adjacent side is cosine theta, and the length of the opposite side is sine theta. What this means is that the unit vector, which we'll call u for unit, the unit vector u that makes an angle theta with the x-axis is equal to, vector u is cosine theta, comma, sine theta. Right, this point right here is cosine theta, sine theta. Now, why is this so useful? Well, sometimes you'll be given a vector, right? You might say, the vector v equals 3, 4. But sometimes vectors are described in terms of their angle and their length, or in terms of their direction and their magnitude, to use two synonyms for those terms. But now, this observation here, how to create a unit vector with a given direction, lets us easily find vectors, the values of vectors, when this information is given. In other words, to find a vector v, not a unit vector this time, but to find a vector v that makes an angle theta with the x-axis and has length L, it's really a two-step process. First, you would start by figuring out the unit vector, the length 1 vector. And the length 1 vector, the unit vector that makes an angle theta, that vector is given by cosine theta, comma, sine theta. Right, that vector has length 1. If you want your vector to have length L, you just have to scale it up. The way you scale it to have length L is you do scalar multiplication. The vector v is L times the vector u. In other words, L times cosine theta, comma, L times sine theta. So if you're given a direction and a length, you can determine what the coordinates of the vector are. Now, it'll be useful to know some of the basic angles. Right, I'm thinking of the angles in the first quadrant. X and Y are both positive. The most popular angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. The way I like to remember these is by creating this little table, and they follow something I call the square root all over 2 pattern. So here, I'm listing these 5 special angles, and then in the rows, I'm listing the values of sine and cosine. You'll notice that in each entry has the form square root of a number divided by 2. Square root of a number divided by 2. So, and the square roots of the numbers are square root of 0, square root 1, square root 2, square root 3, square root 4. In other words, numbers go up. 0, 1, 2, 3, 4 in the sine. For the cosine, it goes in the opposite direction. The numbers under the square root from left to right are 4, 3, 2, 1, 0. And in some cases, you can simplify this. The square root of 0 is 0. So this simplifies to 0. The square root of 4 is 2. So this simplifies to 1. And the square root of 1 is 1. So this simplifies to a half. But I kind of like remembering it with this pattern. Sometimes it'll help you make your problems a little bit simpler. So for example, let's say you're asked to find a vector v with angle 30 degrees and length 6. Well, the way you calculate that is you're going to do 6 times the unit vector that makes an angle of 30. In other words, the vector v you're looking for is 6 times cosine 30, comma, 6 times sine 30. And since this is one of those basic angles, you can simplify this pretty nicely. Cosine of 30 degrees, oops, I think I got these two reversed. Cosine of 30 degrees should be square root 3 over 2, and sine of 30 degrees should be 1/2. My apologies. So this first entry here should be square root 3 over 2, and this should be 1/2. So the vector that you'll get here, wish I could erase with this thing, but it's just a highlight pointer. The vector you're looking for is 3 radical 3, comma 3. So just flip the x and the y here. Similarly, let's say you want to do something a little bit trickier that's not in this table. Let's say you're asked to find a vector w that forms an angle of 72 degrees and has length 5. Well, you go through the same process. So the vector w, that's 5 times cosine of 72 degrees, comma, 5 times sine of 72 degrees. At this point, you might wonder, what should you do next? Well, you can just leave it in this form if you want. If it makes you happy, you can try to simplify this. You can use a decimal approximation if you want, but only simplify if it makes your calculations easier. Right? You can just leave the vector in this form. That is fine. Now, finally, there's 2 special vectors that we should mention because we're going to see these vectors a fair amount in videos that follow. There are these 2 special vectors in 2 dimensions, and they're called I and j. I is the vector 1, 0, and j is the vector 0, 1. These are sometimes called the standard basis vectors for 2-dimensional space. The reason these vectors are special is that any other vector in 2-dimensional space can be written in terms of these vectors, I and j, using the 2 operations we talked about before, vector addition and scalar multiplication. And when you write an equation using these 2 operations, that's sometimes called a linear combination. So for example, let's say we have the vector 3, 4. Right? We can take this vector 3, 4. We can actually use vector addition to break it up into the sum of 2 vectors. The vector 3, 4 is equal to the vector 3, 0 plus the vector 0, 4. And if you were to add these vectors together, be back where you started. From this first vector, 3, 0, you can factor out a 3. You're left with 3 times 1, 0. From the second vector, you can factor out a 4. You're left with 4 times 0, 1. But 1, 0, that's the vector I. And 0, 1, that's the vector j. So this expression can be written as 3 times I plus 4 times j. Now, there is absolutely nothing special about the numbers 3 and 4, other than I like the numbers 3 and 4. You could have done the same process for any vector w. Let's say the vector w is equal to x comma y. You could split that vector up as the sum of the vectors x0 plus 0y. Then from x0, you can factor out an x. From 0y, you can factor out a y. 1, 0, you can replace by I. And 0, 1, you can replace by j. So the vector xy, most general case, xy can be replaced as x times vector I plus y times vector j. I don't know why there's a vector on top of the y. That shouldn't be there. I guess I was getting too excited about vectors. So any vector can be written as a combination of these two. That's why they're called the standard basis. They kind of form a basis for two-dimensional space. Any other vector can be written in terms of them, which, as we'll see later on, helps us express certain formulas in a particularly simple way. But for now, that's probably enough about vectors in two-dimensional space. In the next video, we'll move on to three-dimensional space with x, y, and z. Thanks for watching.